Hello and welcome to this discussion on multiple linear regression and logistic regression. And I'm going to begin by a quick review of the things that we learned about simple linear regression. In simple linear regression, the basic idea is that the sample that we measure is for one variable only. And so here we have our x variable, and we're just measuring one variable as a predictor of y, which is our outcome variable. Now the thing that happens that's different for multiple linear regression, and I'm just going to say MLR, is that instead of only having one predictor variable, now we have multiple predictor variables. And so we learned before that this equation down here, we had y, let's find another color. The y is equal to the intercept plus the slope times x. The main thing that we're going to be doing differently now is that instead of having one slope times x, we're going to have multiple slopes times multiple x's. In other words, we're going to have multiple predictor variables. So here we are in multiple linear regression. And so let me draw that equation one more time. Y is equal to b sub 0 plus b sub 1 x1. And then let's go ahead and add one more of these units right here. Let's just add that and say plus b sub 2 x2. Now we've done a multiple linear regression with two predictor variables, and each one of those predictor variables has its own slope, and each one of those predictor variables then also has the value of that predictor as well. Do you remember how we said that if we know the value of our predictor variables or our independent variables, then we can calculate the value of y for that particular scenario? So given these particular slopes, which is the beta 1 and the beta 2, that's what we're trying to come up with for our populations. What do we think that relationship is? As we increase x by 1 unit, how much does that change y? If we were to say go from age 40 and then we increase that to age 41, does that impact whatever this outcome is that we're measuring here? So a 1 unit change in x, how does that impact our outcome variable? So the same exact principles apply, except now instead of just doing this on a two-dimensional page that we can draw, like we did down here, we can draw that two-dimensionally. There's our two-dimensional drawing. Instead of doing that, now we have multiple predictor variables. A common scenario where we do this, and you've probably heard of this and maybe even participated yourself, is we've said, what is the life expectancy for a person who, and I'm just going to write beta 0 just because that's an intercept, that's a kind of a constant, we almost don't care what that is, who has a blood pressure of a certain level. So let's say x1 is our systolic blood pressure, and then let's say we also know what their BMI is, so beta 2 times BMI. Maybe we also know whether they wear a seatbelt or not. We can add something in that's like that. Times x3, and so on. We can keep going. If you've ever done one of those life expectancy calculators, here we're coming up with a number. We're going to say, oh, I think your life expectancy is probably 85 years, or maybe your life expectancy is only 62 years, and so this is going to be some kind of years. Given that we know a little something about what these other variables are that we measured, the way that these were created, these life expectancy models, is that hundreds, sometimes thousands of people were all evaluated based on these exact same variables. You know, there are probably 10 or 20, sometimes more of those variables, and we could see how those were each related to our outcome variable, how each one was. But then there's an interesting thing that happens with multiple linear regression. And that is that if you put all of these variables into the model together, they really actually also have an impact on each other. And so we see this if we're trying to portray it graphically. Do you remember how, let me see if I can find it right here. Remember how we talked about how we have a certain amount of the variability in y that we can predict by our x variable? And that has to do with kind of this area. Well, let me draw this multiple linear regression idea. If we were to do that same kind of thing, here we have, like, let's say maybe life expectancy, and then maybe let's say smoking is related to a certain percentage of that. Maybe a person's habits in terms of how many fruits and vegetables they eat is also related to that. Whether a person wears a seatbelt, let's say that has its own, part of it's unique, but part of it also overlaps the other things. And so what we find when we have these multiple predictors in a single model is that there actually is some overlap. And because we put them in the model together, what that means is that we can measure collectively all of their impact on whatever outcome it is that we're interested in. And so collectively, all together, as they're impacting each other, what is that collective impact on whatever we're calling our outcome variable? It could be your life expectancy in years. It could be all different kinds of things. So that is the main idea with multiple linear regression. There are two more things that I really need to tell you about multiple linear regression, and that has to do with this idea of R. When we're looking at just a single predictor variable, all we have is one slope and one x variable. The R is very simple. It's simply the relationship between those two variables. But as soon as we've got multiple predictor variables, then what we're doing is we're calculating the relationship collectively between all of these predictor variables and our outcome variable. And so we call that, instead of calling it R, we call it multiple R. Very similarly, we can have a multiple R square. And so that is, again, the proportion of variability in y that is predicted by all of those predictor variables collectively together as they're impacting each other, but there's this big collective impact on our outcome variable by all of them. Now, one of the things that you probably can tell intuitively, but then I'll also bring it to your attention, is that if we're doing something like this where we're trying to figure out what variables do we want to even include in this model, here we are with our model, one of the things is we want to choose the variables that contribute the most, and also the variables that don't overlap 100% with some other variable that's already in the model. And so what we do is we call that model building. And so we have a variety of different ways of doing that. But the big idea is that we want to choose variables that are good at helping us understand this relationship for our outcome variable. But we don't want to include extra variables that really aren't contributing anything new. So in this particular model right here, maybe we had another variable that predicted that part. Well, our other variables that are in the model are already predicting that, and so it doesn't add anything. In other words, when we do that, our multiple R or our multiple R square really don't go up because it's not helping us identify this part over here that we don't know how to predict that piece of it. Models never get to 100%. We're doing really well if we're predicting 70, 60, 70, 80%. So that's kind of the relationship between simple linear regression and multiple linear regression. I have one more thing then to share with you, and that's where this also gets pretty interesting. which is that I need to share with you a little bit about what's called logistic regression. Logistic regression. Logistic regression. Now, with logistic regression, that looks very similar to what we were doing here with multiple linear regression, except that with logistic regression, the main idea to remember is that this outcome variable, this y, is a dichotomous variable. So I'm going to draw the equation here again. Y equals beta 0 plus beta 1 times x1. And then we'll just do it with two variables. We'll do beta 2 times x2. So what happens with logistic regression, because we're predicting some outcome variable that is, I'm just going to say yes, no, is that the probability of this yes happening is not linear. So we have to figure out what to do with this piece of the equation. We have to adjust it or transform it somehow, because regression and all these slopes and those kinds of things only work if it's linear. So let me show you exactly what I mean by it's not linear. Let's say we have some continuous variable, and as that increases, the probability of some outcome occurring, let's just say the probability of a person having cancer, actually follows what looks like kind of an S-shaped curve, like so. That's not linear. So we can't apply a linear model, this is a linear model right here, to something that is not linear. So what we do instead is we take this, and I'm going to have to erase a couple of things. So instead of having just this y equals, let me erase this outside part too. For logistic regression, what we end up with is this fancy transformation that says the probability of a yes, whatever that is, yes cancer, yes cured, yes has this particular trait or has this particular outcome, is equal to, now if you're scared of equations, then I'm going to have to give myself a little more room actually. Let's do something here. Let me give myself a tiny bit more extra space. So I'm going to say the probability of a yes is equal to 1 divided by 1 plus e to the negative of whatever that equation is. So this is this e to the negative, if you remember from your math class, if you take e to something, what that does is it log transforms that particular item. The main thing to remember with logistic regression, though, is that we're really looking at the probability of something happening or not happening. Did they get cancer or did they not get cancer? That's not a continuous variable like what is your life expectancy in years. So we do this fancy transformation. You don't need to know exactly how that works, but just know that we've log transformed it. So now we can use this equation, this wonderful thing that's linear, for a probability. Whoops, come here. Here's the probability. I can't scoot it over apparently. We'll erase those. So the probability of something happening goes all the way from here's from 0 to 1. So here's my probability of 0, and then over that continuum of whatever continuous variable we're looking at, that probability of that event happening goes up. So, oh great, I get to move it. So logistic regression is just like multiple linear regression. Technically, and people always ask this question eventually, can I do this if all I have is like a simple linear regression with only one predictor variable? And the answer is absolutely yes. Logistic regression and multiple linear regression really are based on the same kind of math. underlying behind the scenes, we've just done this transformation. But both multiple linear and logistic regression allow us to add more variables to the model. So I could say even plus beta 3, x3, and on and on and on and on. I could have 20 variables in a particular model. So the vast majority of research that you will read about has some kind of either logistic model if the outcome is dichotomous, or it will have some kind of multiple linear regression model if your outcome is continuous. That's the vast majority of the research that's out there. So just being familiar with if the article says logistic regression, we used logistic regression, okay, well they're just testing if something happened or if it didn't happen. So that's kind of the skinny version of multiple linear and logistic regression. Thank you for joining me.